Okay, we talked about groups, we talked about rings, and that brings us to fields. A field is it's actually something quite close to rings. Here, your underlying structure, you have a ring here, but let's see what are the field axioms. Of course, you have a set and you have two binary operations. First of all, both of the operations, addition and multiplication, are associative. Again, let me emphasize these may not be ordinary multiplication, ordinary addition. I'm just using names. Okay, addition and multiplication are associative. Not only that, they are both commutative. Okay, this is what sets a field apart from a ring. And also there exists two different elements. They have to be different, 0 and 1. Again, these are representative 0 and 1. Not necessarily the 0 we know, not necessarily the 1, the number we know. These are representations of additive and multiplicative identities, okay? Two different elements, 0 and 1, that are additive and multiplicative identities, okay? So in a field, we just represent the additive identity with respect to addition with 0. Doesn't have to be the number 0 as we know it. And we denote the multiplicative identity with respect to, well, multiplication with 1. And again, it doesn't have to be the number 1. These are just symbols that represent the identities. And also, additive inverses exist for every element. Well, because you have an abelian group underlying with respect to addition, but also the multiplicative inverse exists for every element except 0. Okay, so sometimes we denote this as a, uh, a multiplication symbol over its as a superscript along with the multiplication forms an abelian group. Okay, and finally you have distribution. Multiplication distributes over addition. It's not the other way around. Multiplication distributes over addition only. Of course, as I said, an alternative way to see a field is, well, you have a ring and you have commutative property to multiplication. You add an identity element for multiplication, and you add multiplicative inverses for all elements except 0. That's how you obtain a field. But you can see this as two abelian groups. Okay, so a set A with addition is an abelian group, and the identity is 0. And set A except 0 with the multiplication operation forms an abelian group, and the identity with respect to multiplication is 1. Okay? And of course, a field is a commutative division ring. Remember what a division ring is? You have uh, multiplicative inverses except for 0. If you add also commutativity, you get a field. And some typical examples: set of rational numbers, real numbers, complex numbers with the usual addition and multiplication are typical fields. And this structure, the clock arithmetic or the modular arithmetic set, um, so integers modulo n with respect to addition and multiplication as we know them, is a field if and only if n is prime. This is a very important result, not only in abstract algebra, but also as an application in cryptography. We are going to see why this is so, and we are going to see how we can exploit this to come up with uh, cryptographic methods.